Welcome back to the second part of CVX Python package demonstration video. Today we'll try to implement multivariable optimization problem. Let's pose a very simple problem like this. Minimize x1 square plus x2 square. Okay, you all know its solution. It is very simple. Let's see in the Desmos app. So here is the two-dimensional plot. So instead of x1 x2 we have x and y. X square plus y square is this, is like a cone, and you know the minimum value, it is minimum is here 0 0. And let's see how to implement it. Fine. And initially let's don't have any constraint on it. Okay, without any constraint. So let us do step by step. Okay, just wait. First of all, we'll import CVX Py as CP, and now we need two variables. So x1 comma x2 is equal to what we have to do. CP is the package, and inside package we have a function called variable, right? So this is for x1. Then for x2 again we write CP dot variable. Okay, so this defines two variables, x1 and x2. And now we need to create the objective function. Suppose obj is equal to what we want. We want to minimize, so cp dot minimize. Remember that it is case sensitive. You have to write m capital, M-I-N-I-M-I-Z-E, minimize. And now we would like the function. So x1 square, so x1 square is double asterisk like this, plus x2 double asterisk. Fine. So this is our objective function. And then we need to write constraints, but there are no constraints right now. Let's leave it. Now we need to define the problem. So to define problem, you need to define any variable. You can give any name, but let's give a name problem so that we remember that what is the purpose of this particular variable name. Problem is equal to cp dot. Now we need to define the problem. So this is now case sensitive, p capital, p-r-o-b-l-e-m, problem, and objective obj. There are no constraints, we'll not write that. And now we have defined the problem also. Now we'll try to solve it. So problem dot solve. Fine. So you see, when we call the function, the solution is 0 0. This is the minimum value. Okay, because this problem dot solve will solve the problem defined here in the objective function. And in objective function, the objective is to minimize x1 square plus x2 square, and the minimum value is here. And what is the value? So we can write the print x1 dot value, sorry, comma x2 dot value. Okay, and we see that it is 0 0. Okay, so and we know it from Desmos also that 0 0 is the minimizer. Let's try to change this function. Okay, so we can, let's suppose this is the function x1 minus 1 whole square plus x2 minus 3 whole square plus 2. We know from Desmos. Let's try to plot it. So here is this plot. So the minimum value of function is this, that is 2 here. Okay, and this minimum value occurs at y is equal to 1 and z is equal to 3. I mean x is equal to 1 like this, x is equal to 1 and y is equal to 3. Here is this, x is equal to 1, y is equal to 3. Let's see that if we write it here and we change what we need to change. x1 x2 are the variables as it is. We need to change the objective function. Objective is cp dot minimize. Okay, let's call it. So x1, instead of x1, now it will be x1 minus 1 square, then x2 minus 3 square, and then plus 2, right? So let's run it. Then we need to go back to the problem. Problem is called cp dot problem objective. Then we need to solve the problem. Here you see we got the minimum value is 2 as we know. And what are the values of x1 x2 at which this minimum value occurs? Of course it is 1 and 3. So with these very simple dummy examples, we are able to demonstrate that this convex optimization tool is giving the desired results. And the main application of such package will be when you are implementing some complex problem, a real life problem. Let's first try to incorporate constraints in this multiple variable case, and let's even make function a little bit more complex by adding the third variable also. So objective function is equal to, so x1 x2, and let's have one more variable x3. So we need to define then the variables back. So x1 x2, and let's add one more variable x3. So if you are adding third variable, you need to define it like here, cp dot variable. Fine. If you add fourth variable, you need to write it here. Okay, so we have three variables now, and we need to modify the objective function. Let's suppose there is plus x3 minus 6 square. Okay, so now we have three variables. Now we need to define the problem. So cp dot problem objective, and we need to solve the problem dot solve. Okay, we know that again for this function also the minimum value is 2, and what are the values of x1 x2 and x3? So for that we write x3 dot value and run it. So here we perfectly got 1 3 and 6. Now till now what you have learned, you can now handle any multivariable 10 15 16 20 variables optimization problem, of course convex optimization problem, easily. Okay, so let's suppose you have 6 variables. So what will you do? x1 comma x2 x3 x4 x5 x6. Then you write cp dot variable. Okay, and you can copy paste it, and so control Z. So you can now copy paste it 5-6 times. So 2 3 4 5 6. Okay, so now we have 6 variables. Then you can have objective function is equal to cp dot minimize. Let's write some complicated function. Suppose x1 minus 1 to the power 4 plus x2 minus or plus 7 to the power 2 plus x3 minus 9 to the power 6 plus 4 times x4 minus 2 to the power 8 plus 6 times x5 minus 1 square plus x6 minus 11 10. Now first of all, is it a convex function? Yes, it is convex. Why? What is the reason? Because each of the function individually, x1 minus 1 square to the power 4 is a convex, square is a convex, 6 power is a convex, all the even powers of a variable is a convex function, and sum of convex is a convex function. Fine. So now we'll define the problem. Okay, now let's add some constraint. Okay, so constraint, let's suppose that you have a constraint in this problem that x1 plus x2 plus x3 plus is greater than or equal to 6. Let's suppose this is the constraint. Fine. Now we will write this constraint here. So you need to define constraints equal to, so x1 plus x2 plus x3 plus x4 plus x5 plus x6 is greater than or equal to 6. Fine. And now we will solve the problem. So problem, first of all, we'll define the problem with object to obj and constraints. We have to find it. Now we will solve the problem. Okay, so this is the minimum value of this function. Is actually the minimum value of this function is 0. So this is very close 0. It's 1.2 to the power minus 11. So this is actually 0.00000000124. So it's approximate solution, because when the function will be complex, then you know the inside the algorithm gradient descent is running, and gradient descent will give you the approximate solution. And what are the values at which you are obtaining it? So we'll write now x4 dot value comma x5 dot value and x6 dot value. Okay, so these are the values. You see, it should be actually 1, minus 7, 9, 2, 1, 11. But we are getting these numbers again because of gradient descent algorithm. It gives you a very close to the real actual solution. It will not give always exact solutions because of objective function is complex. So I think with this second video, we can say that we have completed a small objective that we will be able to implement any type of constraint optimization problem, provided it is a convex problem. The objective function is convex with the help of CVX Py package. And in upcoming videos, as promised, I will again revisit the KKT because that may not be clear. So I will revise that. Then we will show you one more package to implement the optimization. Thank you.